Morning, good evening. This is the introductory session for the RTOS presented by Takneek Tech Labs. So this is going to be introductory video and we are going to cover some basic concepts which are going to be helpful in our subsequent videos. Okay, so what are going to be cover in this? We are going to cover introduction to RTOS and the RTOS fundamental, some terms related to RTOS, why we need RTOS, and some interview preparation or some topics that are going to be asked by frequently in your interview sessions. Okay, so before going to RTOS, okay, we have we have used this term of operating system. Okay, so RTOS also has one OS in its name. So we all are familiar with the OS. What is an OS? So by the definition, OS is a software that acts as a interface between the hardware and the application. So you have the application, you have the hardware. So to communicate between them, you need a piece of code which is called OS. Okay, so it's not actually a piece of code; it's a decent lines of code. So what are the application? Applications can be your web browser, okay, or can be your MP3 player, or so on and so forth. Okay, so if you want your hardware and application to interact, you need an operating system. So same way we have a refined version or another version of operating system which is called the RTOS. So by definition, RTOS is an operating system designed to execute tasks within a guaranteed time limit. Okay, so if I ask you a question, in your OS, in your Windows OS, or if you are using a Linux machine, does whatever the software you're using or task you are using or you're doing, does that happen in a particular time frame? Answer could be yes, or can be no, right? So sometimes got stuck and you go to task manager and end some tasks. Somehow that's how this works. Okay, but this is the quality of RTOS, that if you are design some tasks and they are running on RTOS, they will execute within a guaranteed time limit. So I'll give you an example. Suppose you have a car, okay, and every car has nowadays called something called a airbag. Okay, so airbag has two functions to do if it is running on RTOS. So the airbag, it should open within a time frame, right? It should open within a time frame in some milliseconds. Whenever the conditions met, your car got hit, that airbag should open within that time frame, right? This is one thing. Second thing is, it should open every fucking time, right? So if your car got hit 1,000 times, it has to open 1,000 times, not 999 times, not 0.001 miss. It has to open 100% accuracy. So that's what we are achieving with RTOS. Okay. Now with general purpose, they are not designed for deterministic timing. This is deterministic time. It should open in milliseconds. It should respond in milliseconds of time or fraction of seconds of time, and that's why we need RTOS. Okay, so what is uh, the difference between an RTOS and a general purpose operating system? So the Linux is a general purpose operating system. I would say Ubuntu that you guys use, or a Windows, or a Mac, Apple based operating system that Apple provides. All those are general purpose operating system. RTOS, on the other hand, are designed for deterministic behavior and a predictive behavior. Okay, so these are the difference. So RTOS are designed for deterministic response. I have we have just gone through what we mean by deterministic response. Okay, this is designed for user convenience. Okay, guaranteed task execution within a deadline with RTOS. With OS, no guaranteed time or execution time. So that's why it has low predictable latency. Sometimes with OS predictability or latency can be high. Okay, it actually it has a smaller memory footprint, but OS has a larger memory footprint. By memory footprint, I mean it consumes more memory, but RTOS on the other hand consumes less memory. Okay, so there are some examples of RTOS, like for ThreadX, VXWorks. Okay, here are the very famous examples of RTOS. So bottom line says, if you want a predictable and deadline based execution, you'll go to RTOS. If you want best effort and user experience, you'll go to general purpose operating system. That clear? This is the bottom line. Okay. Now, what is an RTOS? Now we'll go to the definition that is going to be used for us. That is for understanding purpose. Okay. Because I always think if you know something, it's always easy to build something upon it. So you know OS, now you know RTOS, right? Now we'll go what is RTOS. So is an OS designed to manage multiple tasks and ensure important tasks execute within a predictable time. As I said, within a predictable time. That's the main thing. Okay, so key feature of RTOS, we have seen this. It multiple tasks run simultaneously, predictable timing guarantee, CPU utilization through task switching. We there will be some uh, unknown topics or unknown keywords that you'll face. We'll cover them as we go along with the course. So there's some inter-task communication. For that you'll be curious for the people who are learning for the first time. What is a task? Okay, so what is a task in RTOS? So if you are coming to RTOS, I must assume that you have worked some sort of controller or an Arduino or some 32-bit or 16-bit or 8-bit controller. So you know something like how LED blinks, how sensor read a data, how display update. Okay, so how UART communicate like this. So as I said, this LED blinking, sensor reading task, display task, all these are, if you remind yourself, these are the functions of your code. So if you write a main, or this is one while loop inside main, okay, while one, and this will go on and on and on. So in the while loop, you will have some functions like this: LED blink, or some sensor reading, or some display update, right? What RTOS do, it divides these functions, just it's not actual definition, but for your convenience I am saying, just to get understanding of what task is. We'll see what task is in our subsequent lectures. So all these functions are divided in a smaller portion, which is called a task. So task is an independent unit of execution. What I mean is independent is that LED task generally not dependent on sensor reading task. Okay, and sometimes tasks also communicate with each other, that we will see in the later part. So task is an independent unit of execution managed by the RTOS. Each task performs a specific job and run independently. So this is one very important thing. It's an independent unit of execution. Instead of long program, application are divided into smaller tasks. Okay, so how these tasks, like there's a task 1, there's task 2, there's task 3, 4 and 5 and so on. So how will they execute? One will execute, and then 2, and then 5, or they all will execute simultaneously? What will be the pattern, and who will decide this, that which task will execute first? Because in the super loop we know that LED 1 and then sensor and then display execute in a sequential manner. But what is the behavior in RTOS? So there's a term called scheduler. Okay, so scheduler is uh, designed to control these tasks. Okay, so if you have task 1, task 2, task 3, and task 5. These tasks will be executed guided by the scheduler. Okay, so the scheduler decides how tasks share the CPU resource dynamically. Okay, so scheduler decides which task should run, when it should run, and how long it should run, and what is the which task has the higher urgency. There is something called a priority. So each task, task 1, 2, 3, 4, 5, will get a priority. Suppose the same airbag example. Okay, so the suppose system is doing something, it's showing some light or headlight or something, but when the crash happen, the airbag task has to get the highest priority. Whatever is happening in the background, that has to go, but the airbag task has to get the highest priority. So this is the most urgent task at that time. So who will decide the urgency? The RTOS scheduler will decide, okay, this is the time, the task 3 is urgent, this is the time, task 5 is urgent, and so on and so forth. We'll see the scheduling policies that are being used with RTOS in the subsequent lectures. Okay, so as I said, RTOS scheduler, task 1, task 2, task 3, and it decide based on their scheduling policies that how these tasks will execute together or not. So what RTOS does, task-based architecture, RTOS divide the system into independent tasks. Okay, and the scheduler decides which task should run, when, and how long. Okay, as we've seen, so sensor task, display task, communication task, logging task. So scheduler will decide which one will run first. Okay, so there are two terms. Okay, one is called multitasking and another is called concurrency. So if you have task A, task B, or task C, what is the desirable condition? That each task should run every time. So we want each task to run every time, right? But for a task to run, you need a CPU. And in embedded systems and the system which are cost effective or lesser memory they have uh, lesser computing power. So sometimes they have single core or sometimes they have double core. Okay, so in that case it's not possible to get each task a single core. Okay, so you might have the phone which is 8 core, we said octa core, right? And your laptop can be have 8 core obviously, and so on and so forth. But controller, suppose we have ESP32. ESP32 has 2 cores, right? And suppose we have STM32, the version that we will use in the course, the hardware that has a single core. Okay, so with the single core, there is a problem. One task can run on a CPU, and another task has to wait for task 1 to complete. So if a task A is running, and then it will store its resources, whatever the resources it is using, and then task B come, and then task C, and then again task A, task B, and task C. So this is called multitasking, as I said. But if all tasks are running simultaneously, like together, 1, 2, and 3, this is called concurrency. So this is one very good example of a diagram you can say. So task 1 is executing in this way, task 2 and task 3. So with the time they all are executing together. But with multitasking, task 1 is executing, task 2 is executing is this time frame, and task 3 executing in this time frame. So you can see the time slot is divided for each task, and that task is executing within that time frame, right? So this is called multitasking, and this is very popular approach for the single core or dual core architectures. Okay, so there's one question that must arise. Suppose there's task 1 Okay, this is executing, and the time frame has completed here. And task 2 said I want to execute, but task 1 have not completed its work. So what will happen? So it has to leave the resources as it is, and it has to give the CPU to task 2, right? Then how the task 1, when it will get here, it will get the same resource, because while it leaves the T1, it stores all the data that it was using, or wherever the program counter was and wherever the register was, all these things it was using, it stored that in a memory block. We'll get into more details about it. And then when again it gets CPU, it resumes all those things from there where where he left this, right? So this is called context switching. This is one very good example. Suppose there's a teacher teaching student A math. So teacher is teaching student A maths. Suddenly principal asks for an urgent update. Okay. Teacher write and students A's notebook exactly. Okay. So we have left at chapter 3 question 5 line number 4. And then he leaves for another student to teach science. Okay. And then he completed his science lecture to student B and then came back. And then when he came back, because he has noted down his things that where he left, so he can resume from exactly where he left. This is what the analogy to understand what is context switching. Okay, so task A is running on a CPU. A higher priority task B becomes ready. CPU first save all information of task A. So program counter, CPU register, stack pointer, these things will be saved for task A, and then task A context saved in memory, and then CPU runs task B. And then when again task A came to get the CPU, it can restore, it can see all the things which he has that the task has stored. So this is the call context switching, and this is how uh, the multitasking can be achieved on a single core, because every task cannot complete its operation in that particular time frame. Sometimes it takes longer. So that's how we save the context, and that's why it's called context switching. Okay. So why RTOS? Why we need RTOS? Because why with this question is we have this old approach. So we have a setup loop. Sorry, we have a setup function and then a loop. Okay, and in that we write all our firmware or our code, and then we flash it in the controller and it runs independently in infinitely. Okay, so what is the problem with super loop? So this is called super loop. So in Arduino you have seen setup function or loop function, or in other controller you have seen a main function, and then in the main you have seen a while function, right? While one. This is called a super loop architecture. So the problem with super loop is, suppose this process data took time. Suppose because of some condition it took time more than it required, then this will get delayed. Suppose the data which is need to process got delayed, then display will show misleading information, and that can be catastrophic if you are saying some important decision or some important decision based on that data. That thing can be problematic. So this is the problem with super loop. If one task takes too long, other get delayed. Okay, there are more things that you can read. So with RTOS, what we can use is we can get deterministic behavior, we can get concurrency. You know what concurrency is. Better responsiveness, scalability. What is scalability? Suppose you have 5 tasks and you want to add 2 more. You can add 2 more with same function, and you can adjust your scheduler according to these things. Okay, which is very sometimes problematic in the super loop architecture. Efficient CPU uses, because you can decide which task to run when, which task not to run when, right? So this is one comparison between a super loop architecture and a sorry and a RTOS based architecture. So this is one example code of a super loop architecture: read sensor, problem, process data, update displays, and UART. But if one blocking call, everything freeze. Without RTOS, suppose send data to cloud take 2 seconds to complete. During these 2 seconds, entire system is not stuck waiting. Other tasks get CPU to run. Right? One blocking function affect the whole system. This is the core problem that RTOS solved. If you want to answer why superloop architecture, what was the problem with superloop architecture, and what is the problem that solved by RTOS, this is your answer. Right? So this is one, I think, Arduino based demo that you can see. So white loop, if you blink an LED, read a sensor, print UART, and then block for 5 seconds. So in this 5 seconds, the controller cannot take any input. By any input, I mean if suppose interrupt occur, okay, it cannot respond to that interrupt in this 5 seconds, right? And it cannot read the sensors in that 5 seconds or some expired things, right? So this is one failure condition. So what we do is we'll see all this in detail once we go through the practical sessions. So this is one task, LED task. It toggles LED with 500 millisecond delay. Sensor task is independent and it execute every 1000 millisecond. Same for UART. So when you observe, LED blinks smoothly with every 500 millisecond, sensor read regularly with 1000 millisecond, and UART print continuously with 2000 millisecond. Okay, so this is all three run independently, no freezing. So this is the solution that FreeRTOS has provided. Okay, this is one more myth that comes with RTOS, that it's real time. That means is fast, but it's not. A real time doesn't mean fast. A task must complete within a guaranteed time limit. Predictability and determinism are the core real time feature. So you have to remember two things. Predictability, that it will happen at every single time. Determinism, it has to happen in a given time frame. Right? These are the two things that are important. RTOS does not provide any true parallelism on a single core processor. Okay. Instead, it performs a very fast switching. Right, as we see, task 1, task 2, task 3, task 1, task 2, task 3, task 1, task 2, task 3, it's like this. So it performs very fast switching, creating the illusion of parallel execution, right? So you'll see that you'll get an illusion, okay, everything is happening simultaneously, but it's not happening simultaneously, at least on a single core, right? On dual core or multi-core, the things are different. This is one of the most important concepts understood about RTOS. So it's not fast, it's predictable, and it is deterministic. Okay, so the next is, there are some types of RTOS. So one is called hard time RTOS, another is soft time RTOS, another is firm real time. So a hard real time example we have seen is the airbag. Okay, so we cannot afford to lose a person's life because of some deadline got missed. Okay, so deadline should never miss. If deadline missed, that's a failure. Okay, so those systems are called hard real time. Okay, so airbags cannot miss, medical devices cannot miss, pacemaker, if you know, if pacemaker miss uh, one or two times, then a person can die, right? Flight control systems, you cannot miss any single deadline. With the soft real time, what happens? With occasionally you can miss. So video streaming, audio streaming, online gaming. If you're you've seen, like, you got latencies in all these games and all, a video streaming all. So that is acceptable. It's not catastrophic, right? And there is firm real time. So late results are useless but not dangerous. Okay. So sample sensor reading, stock market data, weather forecasting. Suppose some stock is at 100 and it reached 101, but you are not updated and you made your decision based on this 100. So that is not useless, but I mean, results are useless but not dangerous. So this is the firm real time. Okay, the difference lies in the consequences of missing the deadline. Hard, it's catastrophic. Soft, it degrades the quality. Firm, wasted computation. Okay, so these are the types of uh, RTOS. Okay, so there is one very famous question that uh, comes for an RTOS interview. If you sit in an interview which covers RTOS, so I say why we say RTOS is deterministic. This is the heart of RTOS. The system behaves predictably. Same input always produces same response within a known time. Just remember this line. This is the core of this lecture. Same input always produces same response within a given time. Okay. Deterministic system. Sensor task run every 10 millisecond, consistent and predictable timing. Non-deterministic means it can take 5, sometimes 20, sometimes 2, sometimes 50. But that is why determinism is used. So suppose a motor is controlling or robot balancing. Suppose you see a drone flying, right? You've seen a drone flying. If some wind came, okay, in this direction, and your drone didn't stabilize, it will topple down, and the operations will can like it get damaged. So you need stabilization at every same response and at the same time, right? System may fail, unpredictable timing can be catastrophic. So this is one very important question that I was saying. How RTOS provide determinism? So you'll see, first you'll ask, what is an RTOS? So you'll say, okay, RTOS is this. Why super loop versus RTOS? So you say, okay, what was the problem with super loop? You solve it. And what is the RTOS? So you'll say it provides a determinism and predictability. Okay. So the next question arises, how they provide determinism. So RTOS achieve determinism behavior through four key mechanisms working together. So one is scheduler. So scheduler decides which task should run at what time. Okay, so this is the quality of scheduler. Priorities. So every task gets CPU first. Which task which gets CPU first? So the highest priority task will get CPU first. Who will decide the task has the highest priority? Scheduler will decide. Okay. Tick interrupt. We'll see what a tick interrupt is, but for as of now, you will understand. This is the watch for RTOS. So every second, every millisecond is calculated based on this interrupt, and based on that, it calculate. Okay, it has to behave. Uh, it has to produce the output in 10 millisecond, and how it will calculate 10 millisecond based on this reference. Okay, we'll see that in detail. What is context switching? You have seen that task 1, task 2, task 3, and how the task 1 save the data, and then task 2 get the CPU, and when task 1 came again, how it can get this context which it was executing in its previous execution time. Okay, so these four mechanisms work in harmony to ensure predictable, timely execution of all tasks. So if you get asked how RTOS provide determinism, you'll say scheduler, task priorities, tick interrupts, and context switchings. These are the possible questions that can be asked in your RTOS interview. Okay, so one is the what is RTOS, why the super loop was the problem, and what RTOS is solving, what RTOS provides. Okay, so it provides determinism, how it will provide. These are the things that how the RTOS provides determinism. Okay, so practical RTOS design principle. Most efficient RTOS systems do not keep tasks running continuously. Okay, so the best practice to design a task is you run quickly, perform work, block or sleep. What is block or sleep? We'll see together, but we'll see further. But you understand, okay? It came quickly, it worked, and it gone to sleep. and it's not working, it's not utilizing CPU, it's not utilizing CPU, and then whenever it got called, the conditions happen, it will come back, run quickly, and then perform work, and then go to sleep. That's how the real design should work. Okay, keep task running in infinitely busy loop without blocking this base CPU and prevent other tasks from running. Key insight: a well-designed RTOS task spend most of its time in block state. This is what makes RTOS efficient. Tasks only run when they have works to do. So there are some advantages of RTOS, but there are some disadvantages of RTOS. Okay, so advantage we have seen: better organization, true multitasking, better timing, faster response, cleaner code. There are some disadvantages also. One is it brings more complexity. So it's easier to maintain a super loop code than to maintain a RTOS code. It consumes more RAM, right? Debugging makes harder because tasks get switched and you have to see the logs and many more things come into picture. Context switching overhead, this comes into picture. A smaller CPU overhead added. So these are the advantage and disadvantage of RTOS. So this is some historical background and what are the things available for RTOS. So the RTOS got introduced in 1970s. Okay, first RTOS. Sometimes everybody claims they have XYZ is the first, Y is the second, but QNX is sometimes named as the first RTOS, and then Trojan and RTMS, VxWorks, PSOS, Nucleus ThreadX, and in 2010 FreeRTOS was introduced, and then multi-core RTOS, and then we have too much of RTOS nowadays. So the most famous ones are the FreeRTOS, the Zephyr you might heard of, ThreadX, VxWorks, QNX. These are the companies that are backed by these. I mean, these RTOS are backed by these companies. Okay, Nucleus is backed by Siemens and Emboss is backed by Sega. Okay, most popular RTOS is, and the champion is FreeRTOS. As the name suggests, it is free, and the licensing thing we'll see when we start working on the code. So we'll see what it is, why it is called FreeRTOS. Okay, and what are ThreadX and Zephyr and QNX and VxWorks. We'll see in future lectures, but our major focus will be on FreeRTOS. Okay, we will cover FreeRTOS on this board. This is an ESP32 board plus on the STM32 board. Okay, so ESP32, what is the advantages of using ESP32 is the learning will got faster. Okay, why? Because it runs FreeRTOS in the background. We'll see how it works in the next classes, but it got easier. And if you want to go into nitty-gritties and details, if you want the details, the devil lies in the details. If you want to meet the devil, so you have to go to this STM32 and then we'll tear down every macro, the function, the calls, APIs, and everything. We'll see that and how it interacts with the configuration file, how the macros works, how the priority comes, scheduling, context switching, how the inter-task communication works, queue, semaphore, mutex, event groups, software timers, memory management, and we'll do a real world project in the finishing. So thank you for listening to me. I intentionally didn't cover these 2 or 3 slides. You can see the description and get the details. My point is, so if you go to any RTOS course, okay, so in 10 hours or 15 hours, they'll just rush you to some uh, calls. This is the function that is used. Do this X task create and then run it, and then they have some predefined example, and then in 15 to 20 hours, they'll finish the course. Okay, what happens is you'll get the certificates, okay, but you didn't get the knowledge. Knowledge which task to get the priority high, which task to get the priority low, how the mutex works, how the semaphore works, how the tasks really communicate, where to use mutex, where to use semaphore, how the queues are used, and what are the internals of those things. Not only calling the X task create or queue create or semaphore, these are just function calling things. Okay, so in the era of AI, people want more from you. So only having a super loop experience in your resume cannot be a good thing to get into a job market. So I'll uh, suggest you to equip yourself with a RTOS. Okay, and the best RTOS to get learn and get into RTOS is FreeRTOS. Okay, why is easiest one? I will explain you in the subsequent lectures. But when you'll go into these RTOS, if you go to Zypher or TEDx, you'll understand what are the complications involved in those things just to get the first task running. Okay, so first get the concept right with FreeRTOS, how the things works, how the RTOS works, scheduler works, and then go to the Zypher or QNX or VXWorks or whatever you want to do. Right. So this is the first introductory lesson from Takneek Tech Labs. Thank you for your time. We'll soon be uploading the further lectures. Please like, share, subscribe, and yeah, thank you. Have a good day.